Good morning. In the last lecture, I introduced you to the concept of moment distribution and the physical reasoning behind how moment distribution works in terms of relatively removing the clamp at the joints. Okay, so that's how the moments get distributed, and ultimately we see that it will always converge, because as you release the rotations at the joints at which your moment equilibrium has to be maintained, as you release it progressively, you are going to keep releasing it till you get equilibrium. Okay, so ultimately the entire moment distribution procedure is an iterative procedure that ultimately gives you equilibrium at all the joints, satisfies all the equilibrium equations. Okay, so now let us look at this thing, and note that what we are normally considering here is the moment equilibrium. Okay, in fact we are currently only looking at moment equilibrium. Okay, let us now look at certain other aspects to it. Remember, I talked in the last lecture that how do we account for the modified member that we had. Okay, so let us look at this. Let us look at this particular problem itself. Same problem, excepting that this time I am going to say that, well, I will consider AB as my clamped, but BC I am going to consider it as the modified member. Okay. Now if I consider it as the modified member, what happens? So for A, B, B, C. So here we have this, and here we have this. So first and foremost, okay, I can calculate the fixed end moments. Fixed end moment at AB is equal to plus 1 is equal to minus. Now I am going to calculate the fixed end moments at BC and CB as if they did not exist, as if this was clamped. I am going to compute it that way. It is not, but I am going to compute it. So okay. Now remember, what was the modified fixed end moment here? The modified fixed end moment remember that? We had computed this. Now my point over here is this, that isn't this the same as my doing balancing the force here and then carrying over half, okay, which is basically plus 208.3. Doesn't it? You see, this is almost exactly like, and once I release this, that's it. Now this has gone to 0 and it will never come back again because this is a roller. Okay, this we can do even in fixed end moment, in this thing in which the fixed end moment we compute as if this was fixed. Okay, then do the balance over here, put it to 0, transfer it over here, and then solve the problem. But let us look at what are the other things. These are the fixed end moments. What is MAB is equal to here 4 E I by L I call it as theta AB. Since theta AB is a fixed end, this goes to 0 plus 2ek theta BA, which is of course there, okay, and plus the fixed end moment. Okay, so this one has MBA has that exists. Okay, but now what is, so these are the moment deformation relationships for AB. For BC, what is it? It is given as MBC is equal to 3EI by L. So this is KAB, 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 KAB. This is EI by L for BC, 3EK BC into theta BC. That's it. There is nothing else, and we here MCB is equal to 0. Okay, so can I write this in this fashion? I'll write this in MBC is equal to 3/4 of 4EK by C theta BC. Okay, and if you look at it, what is MBA plus MBC? MBA plus MBC is going to be equal to, so the moment distribution MBA is equal to 4E KAB plus 4E KAB plus 3 by 4 4E KBC. Remember that the 4 cancelled, E cancelled, and that's how we got KAB plus KAB plus KBC in the other case. But here this becomes plus 3 by 4 KBC. So therefore, for a modified member, we can define a KB modified, which is equal to 3 by 4 KBC. If we do that for the modified member, then MBA is equal to KAB upon KAB plus KBC modified, and MBC is equal to KBC modified by KAB plus KBC modified. So the only thing that happens is when you have a fixed hinged, the modified K becomes 3 by 4 KBC. Is that clear? Okay. Now what about the carryover factor? The carryover factor MAB is still equal to half of MBA. So the carryover factor from MAB to MBA is still half. This is fixed, so therefore this doesn't go. Okay. However, what is MCB in terms of MBC? 0, because MCB is 0. So when you have a modified member, the carryover to the other end is 0. There is no carryover because moment cannot be carried over. So with these modifications, let's see how I can solve this particular problem that we have. So in other words, for a modified member, as far as computation of fixed end moments will come, we will see, let's not try to make a differential, because we will see that this is actually incorporated into the modified, into the this thing. So as far as the fixed end moments are concerned, there is no difference from the original. Okay, fixed. However, for the modified member, the stiffness is modified to 3/4, and the distribution factors, this is into MB. So the distribution factors are equal to this. So if we modify it, then we can continue using the same, and the only other thing is that in a modified member there is no carryover. Okay, with this new concept in mind, let's see how this particular same problem that we have, how we can solve that problem. So let us go through the steps. We've already calculated the fixed end moments, so let us now go through the steps. Again, AB, BA, this is member AB, this is BC, CB. Now note that let us see what the distribution factors turn out to be equal to. Let me just do the distribution factors at this point. What is KAB? It is equal to I by 10. What is KBA equal to I by 10? What is KBC equal to? 3/4 I by 10. What is KCB equal to? 0. Okay. So therefore, the distribution factor BA is equal to 1 over 1 plus 3/4, which is equal to 4/7, and DBC is equal to 3/4 upon 1 plus 3/4, which is equal to 3/7. So the distribution factors, since I am considering BC as modified, this is 4/7, this is 3/7. This one, no distribution because it's a fixed end, and here distribution is 1. Okay, there is no carryover in this direction. However, I'm going to say that only for the release of the fixed end moment is there a half carryover. Here there is a half carryover. Here there is no carryover in this direction because fixed end is not to be released. Okay, so now let us put down the minus 115 plus 416.7 minus 416.7. Okay? So now the first thing is, since this is the first thing we do is put plus 416.7, put this equal to 0, carry over here, this becomes plus 208.4. Okay? And this one is a first off case. Then we look at, so this has gone to 0. This is not to be considered again because it's a modified beam. Okay? So this is just the fixed end moment alone is released. And understand that this is identical to doing FEM BC minus FEM CB by 2. So we could have done that. We'd have got this. Same thing. Okay? Once we've done that, this is the unbalanced. What's the unbalanced? Plus 625.1 minus 115.2. This is the unbalanced. So this needs to be balanced now. So balancing will be done as 4 upon 7 and 3 over 7. So this becomes, this is positive, so this is negative. So negative 291.2 minus 218.7. That's the net unbalanced. So once I've done that, that's balanced. Then I have a carryover here. The carryover becomes plus 145.6, sorry, minus 145.6. Now let's look at it. So this is the first level of carryover. Any unbalanced left here? No, this is 0. Here we've balanced, we've carried it over. There's nothing else. We've ended it. We've finished it off. And so this one turns out to be equal to plus 27.2. This turns out to be equal to minus 406.4. This turns out to be plus 406.4. This turns out to be 0. This is what we get. There's only one iteration. Why is there only one iteration? Well, why? Because since this is released, this is the only one clamped. As soon as we release it, okay, we've got balance here. That's it. There is nothing else. Theta CB can go any way it decides to. Okay? So that is the reason why, if you look at this, how this is spectacular. We had 9 steps to get to convergence, and by using the modified beam, we just did it in one iteration and reached the solution. Okay? Now, it's never going to be this spectacular, but this illustrates how using the modified element actually helps in speeding up the moment distribution convergence process. Okay? So therefore, to review, I just want to say that for a modified member, you take the, instead of, for a regular member, K is equal to I upon L. For a modified member, K is 3/4 I by L only at the continuous end. Is that clear? And you can only apply the modified if the other end is a support. So at a support, you never have another member. So that does not come into the picture. Even if you have, note that here you have a hinge support at B also. But since there is a continuity, you cannot take moment. You know that. You've already seen that, and I don't want to belabor that point again and again. So all you have to do is, for the modified member, at the continuous end, you just make the stiffness 3/4, and so the distribution, you use the modified stiffness in the distribution factor computation, and secondly, there is no carryover in a modified member ever. Okay? So this, in essence, is the application of the modification or the modified element in the moment distribution method. Okay. Now let us look at a kind of a situation where again I'm going to take the same problem, right? I'll take the same problem in the earlier case which we had done, where we had we had this situation. This support went down by 0.03 meters, 3 centimeters. And we had to find out the moments at this point. Okay. So here, if we look at it, what are the fixed end moments? Well, let's see. Due to this 0.03, you're going to have fixed end moment at AB is going to be equal to 6 EI upon L squared. And since we were given, I'm solving the same problem, E is equal to 209 Newton per meter squared. I was given as 2000 into 10 to the power of 6 meter fourth. Okay, so substituting these in, we got that the fixed end moments here was plus 720 kilonewton meter. Similarly, fixed end moment at BA was 720 kilonewton meter. At the other end, what did we have? At the other end we had, I'm going to consider PC the same, so it's going to be just the opposite. So you're going to have minus 720 kilonewton per meter, and this is equal to the fixed end moment at CB. Okay, and now I'm going to use the modified member. So I'm going to just, all that happens due to support settlement is that I use the same one that I've just used. So I'm not going to go through the same points, I'm just going to write them down. This is 4 by 7, 3 by 7, okay. This is 1, this way 0, this way only to release the fixed end moment we have half, this way we have half, this is a fixed end, this way it's 0 because it's a fixed end, you don't carry over from a fixed end, and this is plus 720, this is plus 720, this is minus 720, minus 720. These are the fixed end moment. First, balance out at CB for it equal to 0, bring it over here, plus 360. Okay, so now the next step is that what's the unbalance here? You will see that this two balance each other. It's the only left unbalanced is this. This has to be divided as 4 upon 360. What you get is 200 and plus 360. So 4 upon 7 of 360. This goes 5 and 51.30, so 51.4. So this becomes 200 and 4, 205.6, and so this becomes, this is minus, so this becomes minus 154.4. This is the balance. Then you have half here, so this becomes minus 102.8. Okay. $102.8. So that's it. That's done. So this is it. So just due to this alone, it's going to be plus 600 and 17.2. This is going to be equal to plus 500 and 14.4, and this is going to be equal to minus 514.4 is going to be 0. Now this is due to the settlement alone. If I superpose, all I need to do is add the ones that I have got from before, which was plus 27 minus 406.4 plus 406.4, 0. So if both the force and the rotation occur together, what we get is 644.4. Here we get plus 108.0, and here we get minus 108.0 and 0. So if both the settlement and the loads are together, you do it separately or you can do them together, I don't care, you are going to get this same thing. Okay? So understand that support settlement, all that support settlement does is that, and a known support settlement, it introduces fixed end moments, and we do the distribution exactly in the same manner as before. Okay? So now let us look at another problem. Just to go through the steps, up till now we've only looked at two members. Let us look at what happens when you have multiple members coming into the picture. Okay, so I'm just going to go now take up a particular problem, a realistic problem, and let me take it up. Not very well done. Don't go by what I have drawn. Take down the numbers that I have. 30 meter, 40 meter. EI is a constant, so this is EI, EI, EI. Okay. Then on this we have .4 kilonewton per meter. Here at the center point we have a load 40 kilonewton meter. Here at the center point we have a 40 kilonewton meter. Okay, so for this one we need to find out the end moment and then the bending moment. Once you have the end moments, the bending moment diagrams are obviously. Okay. So A, B, C, D. Okay. So the first and foremost, compute. So I'm just going through algorithmically, I'm going through the steps that you do in the moment and applying the moment distribution method to a beam problem. Okay. Today we are only going to be looking at beam problems, and from the next time onwards we'll see how to consider a frame. Okay. So let's look at a beam. So the first step is calculate fixed end moments. And when you take fixed end moments, you don't worry about whether it is a modified member or not. You calculate fixed end moments as if everything was fixed. So for this one, it's going to be equal to 40 into 30 divided by 8. So the fixed end moment is going to be equal to plus 150 kilonewton meter. Fixed end moment at BA was equal to minus 40 by 30 upon 8. So minus 150 kilonewton meter. Fixed end moment at BC is equal to 2.4 into 40 squared upon 12. So this is equal to 1600 into 0.2, that is plus 320. Fixed end moment CB is going to be equal to minus 620, and this is equal to FEM CD, and this is equal to fixed end moment at DC, because they are the same thing. So let me then compute the distribution. So now AB is a modified member. So K of AB is a modified member, so KAB, now KAB is equal to, this is for the member, for the member is going to be 3/4 I upon 30. So this is equal to I by 40. KBC, since BC is continuous, is going to be I by 40, and KCD is going to be 3/4, because D is a roller, so it's going to be modified. C is going to be the continuous end, fixed end, D is going to be the roller. In AB, A is going to be the hinged end and B is going to be the roller. So if you look at it, distribution of BA is going to be KB plus KBC upon the summation, which is going to be half. DBC is going to be half, and at C it's going to be I upon 40, I upon 40. So DCB is going to be half and DCD is going to be half. Okay, so having done that, let us see what the whole thing comes out to be equal to. Let's put it. Note that carryover BA is equal to 0, carryover BC is half, carryover CB is half, carryover CD is 0, everything else is automatically 0. Okay, so with these kinds of things, putting them in, AB, BA, BC, CB, CD, DC. Okay? So what happens over here is AB. It's a hinged end. There's nothing that happens. There is only a 1/2. That's only once. This way it's 0 carryover. Here we have half, half. Here we have half, half. And here this is 0. The only thing that we have is half for 1. This way it's 0. Here this is half, half. Okay? So now I'm going to actually, and what are the fixed end moments? This AB is plus 150, okay, minus 150, this is plus 320, this is minus 320, and if you look at CD, this is plus 150 minus 150. The first step is to release these two. So I'm going to put minus 150 plus 150. These are finished, and all that we do is take this here and put minus 75 here and plus 75 here. Now this is the one that we need to distribute. So if you look at it, 225 and this is 320. So the net unbalanced is plus 95. So minus 95 has to be distributed. So we do minus 48 minus 48. Similarly over here we do that same. See, now here this is the point that I was trying to make, and this is the problem. I have taken up this problem to show you how we don't do it one after the other. We look at every joint and distribute whatever is the unbalanced moment at that point in one shot. So again here at the same point, I'm not going to be doing the carryover. First I'm going to look at the unbalanced, look at what we have here. This will be 47. Okay, now I'll make this 47 and this 48. So here also I'll make this 48 and this 47. You will see that the same unbalanced moments come up. Okay, and now once what we've done is we've done both of them together. Now we do the carryover. There's no carryover here, no carryover here. However, there's carryover here and here. So we have minus 24, minus 24. Now we unbalance these. So this is going to be plus 12, plus 12, plus 12, plus 12. Balance. Now no carryover here, only carryover here and here. This is going to be plus 6, plus 6. Okay, so now we need to do, so it's going to be minus 3, minus 3, minus 3, minus 3. That is what it is. And then we do again carryover. Carryover is going to be minus 1, minus 1, and for all practical purposes when I distribute that, I'm going to distribute plus 1, 0, 0, plus 1, and that's it. It's over. No other carryover, nothing else. So you reach the end. Now when you do this, add all of them up, 0, add all of them up. Minus 225 and this is going to be equal to 225 plus 47 is 272, minus 272 plus 12 is minus 260, minus 263. This is 225, and 47 is 265, 272, 272, 260, and this thing is equal to 260, and minus 3 is minus 263, minus 262. This is going to be plus 262. Okay, this is going to be minus 262. This is going to be plus 262. This is going to be equal to 0. Now, once you have this, you've got the member and moments. You can draw the. You can do the distribution. Now, the point that I'm trying to make over here is that note that I did this problem just to show you that when you actually have a kind of, in reality, you don't do release one, then clamp the other one. You know, that procedure, once we have established it, now you cannot tell what is happening here. I'm kind of simultaneously releasing both, okay, and then looking at the effects, then releasing, taking effect. You know, so physically understanding this is very difficult. Okay, physically this doesn't make sense, but you see, you have to understand that in the moment distribution, the steps are the following. First, compute the fixed end moments. Now, even if you have a modified member, you compute the fixed end moments as if it was a fixed member. Okay, so the fixed end moments are computed as if every member was fixed. Then the next step is actually computing the stiffnesses of each member. Now, in this particular case, when you compute the stiffnesses, then what you do is, the first step that you do is you actually go ahead and compute the stiffnesses based on whether a member is the original member or the modified member. Okay. So, once you have that situation, so therefore, if we look at this, in this particular case, we computed, when we computed the fixed end moments, we computed the fixed end moments as if all A, B, B, C, C, D were all original members. So, fixed, and we computed the fixed end moments. Actually established the fact that AB is a modified member, BC is the original member, CD is a modified member. So, while computing the stiffnesses, that is where we take into effect that AB is a modified member. So, it's BA basically KBA is 3/4 of I upon L. Okay. BC is a normal member, so it's I upon L. CD is a modified member, and then the distribution factors are computed based on the modified members, and then the carryover factors of course depend on whether it's a modified member or a regular member. Okay. Then the first thing that we do is we've computed the fixed end moments based on fixed. So, the first thing that we do is actually release the two end releases and carry that over once only, and that's it. Then these two are finished because now nothing goes back to them. Okay. So, now what we have to do is we look at both the members. So, in other words, how many ever joint continuous members joints we have, we look at their distribution to the unbalanced forces at one shot. So, we do all the distributions at one shot. So, you will see this, if there are more members, all would be distributed. Then the next phase is the carryover phase. So, you carry over everything that you have to. In this particular case, only the carryover is here because there is no carryover on the other side. Then once we have finished the carryover, then we look at all the unbalanced and do the distribution. So you have fixed. The first is the modified member carryovers, then distribution, carryover, distribution, carryover, distribution, carryover, distribution, till we hit a situation where the carryover is 0, and so ultimately the distribution is ended, and that is your final member force. Okay? So this in essence is your overall moment distribution method as we see it for beams. So if I want to review what I have done today, I have looked at the moment distribution method as applied to beams. We have looked at how modified members can be incorporated into the moment distribution. Okay. We have seen the physical understanding behind the moment distribution method, and then we have applied it where we actually do it over in a distribution phase, carryover phase, distribution phase, carryover phase. Okay. We saw how to consider support settlements into the entire consideration. The other point I would like to make is that even if you have temperature effects, okay, the temperature effects are again local effects which only give rise to fixed end forces. Everything else, the moment distribution procedure is not different whether you have a load in a member or whether you have temperature in a member. Okay. So in other words, today what we have done at the end of this lecture, you should be actually able to solve any problem that you have for a beam. Okay, you should be able to do the moment distribution method. Now what I want to do is I want to give you a problem so that you can solve it yourself. Okay, so please take a note of a problem. Let me give that problem and you have to do the problem yourself. This is the structure, and I want you to solve this particular problem, okay, and get the member end moments, and once you get the member end moments you can draw the bending moment diagram. So I ultimately want you to get member end moments, okay, and ultimately the bending moment diagram using all modified stiffnesses and distribution factors that you can use in this particular case. Okay? So after today, I hope you will be able to apply the moment distribution method to beams for any kind of situations. I have given you this problem as an exercise. You have to do it and satisfy yourself that you understand the moment distribution method. From tomorrow, I am going to spend a few lectures looking at how to apply the moment distribution to frames. Now, when we looked at the displacement method, we saw that whether it was a frame or a beam, the method was really the same. The only thing is that in a frame, you might have to write down certain equations, equilibrium equations related to displacements. Okay? Otherwise, the procedure was identical. In the moment distribution method, you will see that in frames that have displacement degrees of freedom, the entire procedure is very, very different. I will first start off by looking at a frame and see how we can do the moment distribution where it does not have a displacement degree of freedom. Okay? We'll look at that, and then we will go on to see how to modify the moment distribution method so that you can consider displacements or what are known as sway in a frame. Okay? Thank you very much. I hope you have understood the moment distribution, and please do solve this problem that I have given you and come back later and with confidence. Thank you.